In this video, I will show you how to maximize network bandwidth. Your server throughput will improve as it will use available network capacity in an optimal manner. It will also reduce queuing delays and help to minimize latency, resulting in more responsive network communication. To better understand what's going on, we'll first very briefly go through the basics of TCP operation. My name is Philip. Let's get started. If you want to know what parameters to change and don't care about the theory behind it, please go here. Otherwise, let's briefly talk about three fundamental TCP features: data integrity, flow control, and congestion control. Just enough to get you started. Let's talk about data integrity. If you ask any IT professional what is the difference between TCP and UDP, they will most likely tell you that, unlike UDP, the TCP has a mechanism to ensure integrity of the data and guarantees that the data is not corrupted during transmission. That is absolutely true, and it's a fantastic feature of TCP protocol, making it run the internet. Let me briefly remind you how it works from a high-level perspective. In order to achieve this, TCP uses few mechanisms. Let me introduce a concept of TCP segment. By TCP segment, we mean TCP header that contains metadata and TCP payload that has the actual data. In TCP header, there are various fields like source and destination ports, sequence and acknowledgement numbers, data offset, reserved bytes, TCP flags, window size, checksum, urgent pointer, and options. We'll talk about some of them later in the video. First of all, for every segment, TCP calculates a checksum and stores it in the checksum field inside the TCP header. Once the receiver gets the segment, it will perform his own calculation of the checksum and compare it to the value stored in the checksum field of the received TCP header. If the checksum does not match, it will indicate that the segment has been corrupted and needs to be discarded and retransmitted by the sender. The receiver knows about the corruption, but how to notify the sender to retransmit the data one more time? Here comes yet another TCP mechanism, that is sequence numbering and acknowledgements. Basically, for every segment of data, TCP will assign a sequence number and put it in the TCP header. If the sequence number of our first segment is 100 and the length of the packet is 200 bytes, then our next sequence number will be 300. So basically, the difference between sequence numbers shows how much data was sent. After we send a segment on the wire and the receiver gets it, it will send an acknowledgement back, putting the sequence number of the next expected byte in the acknowledgement number field. Basically, with sequence numbers, the sender tracks how much data was sent to the receiver, and with acknowledgement numbers, the receiver confirms how much data it received. This has few interesting features. First of all, the receiver doesn't have to acknowledge every TCP segment. Let's send another segment with sequence number 300 and 500. The receiver can acknowledge both segments with a single acknowledgement of the next expected sequence number, that is 700. An acknowledgement informs the sender that all bytes up to the acknowledgement number have been correctly received. Usually, we see an acknowledgement on every other TCP segment, assuming all is working correctly. Getting back to retransmissions. Following events can trigger a retransmission. First one is timeout. Every time a sender sends a packet, it enables a timer. Basically, the sender expects an acknowledgement with a certain time period, and if acknowledgement is not received, it will resend the segment automatically. Second event that can trigger a transmission is receiving 3 duplicate acknowledgements for the same segment. In other words, if the receiver did not get a certain segment, but did get next segments, it will keep acknowledging the previous segment for every segment it receives until the sender retransmits the missing segment. Thanks to that, the sender does not have to wait until timeout expires, but can perform so-called fast retransmit and send the missing segment immediately. There are certain mechanisms like selective acknowledgements where the receiver can notify the sender about future segment that it received so that the sender can figure out exactly which segment is missing, but we'll not talk about it today. Lastly, the receiver stores segments received out of order and can rearrange the data based on the sequence numbers before passing it to the application layer. As we know, packets can take different routes, network congestion can happen, so the data can arrive in different order that it was sent. TCP features like checksumming, sequence and acknowledgement numbers, reordering and retransmissions guarantee integrity and corruption-free data. Another TCP feature does not immediately come to mind when thinking about TCP is flow control. In order to understand what flow control is, let me draw a simplified diagram. We have a sender and a receiver. On the sender side, there's an application that wants to send data. For that to happen, it will push the data to the sender socket buffer, also called transmission buffer. This is a special place in the memory used by operating system to temporarily store outgoing data it got from the application. It then goes to the network card buffer where it's put on the wire. On the other end, we have a receiver that grabs the data from the wire, puts it in the network card buffer, then to the socket buffer, also known as receive buffer. That is a region in memory used by the operating system to temporarily store incoming data before it's read by the receiving application. So we have two socket buffers, sender buffer and receiver buffer, and also two buffers on the network interface called the ring buffer. We can check the maximum and current size of the ring buffer with ethtool command. NIC buffer is not dynamic, but can be adjusted if needed. We can also check the default socket receive and send buffer for TCP connections with sysctl command. R stands for receive buffer and W stands for send buffer. First number represents the minimal size of the buffer in bytes. That is allocated in case the system is under memory pressure. Second parameter is the initial buffer size, also called the default. Last parameter is the maximum buffer size that can be allocated for a socket. Please mind that maximum buffer size cannot exceed mem_max parameter that represents the maximum size of send and receive buffers that can be allocated system-wide for all types of network sockets, including TCP. So, if you'd like to increase the maximum socket buffer size for TCP, you need to increase the global limit first. The buffer size can be dynamically adjusted between the minimum and maximum value by the operating system during the lifetime of TCP connection. We can check the actual send and receive buffer of a particular TCP connection with the ss command. RB shows the receive buffer in bytes. TB shows the send buffer in bytes. As you can see in this example, the receive buffer size has been dynamically resized to 10 megabytes and the send buffer is at initial 87K. SS command shows yet another interesting information, that is receive and send queue length. Basically, these values show the amount of data in bytes currently queued in the socket buffer. High numbers in the socket receive queue may indicate that the application is not reading data fast enough. That's called a slow receiver. If you see a high number in the socket send queue, then most likely the application is producing data at higher rate than the network can transmit or receiver can process. As we know the very basics of what socket buffers are, let me explain what TCP flow control is. This particular mechanism prevents receiver from being overwhelmed with data. It allows the receiver to regulate the rate at which it receives data from the sender, preventing buffer overflow and potential data loss. I will oversimplify the example, but let's imagine we have a sender and a receiver. The receiver has a socket receive buffer that is 30K, that is already half full and cannot be increased by the operating system. In such case, the receiver can advertise that the window size is 15K. How it's done? There's a special field in the TCP header called window size. It indicates the number of bytes the receiver can currently receive and store in its buffer. It's initially advertised during TCP connection establishment, but it's adjusted dynamically during the communication. Now the sender will send segments of data until advertised window size. So if the advertised window size is 15K and the maximum segment size is 1460, then the sender can send up to 10 segments and then needs to wait for the acknowledgement from the receiver. This ensures that the sender does not overwhelm the receiver with data. Receiver will acknowledge received data by sending an acknowledgement back to the sender to confirm the data was received. Receiver will also update the window size, informing the sender that there's space available in the receiver's buffer and allowing the sender to continue transmitting data. This particular mechanism is called TCP sliding window, as the window slides forward, allowing the sender to transmit new data. Like we said, the TCP window updates are dynamic, so at any given time the receiver can notify the sender that it has more space in the buffer by sending an update with increased window size. Also, the other way around, if the buffer is close to full, the receiver can send an update with reduced window size so that the sender will slow down the transmission rate. A receiver can also send a packet with the window size set to 0. This indicates that the sender cannot send any more data and needs to wait for the receiver to send a new packet with updated window size. There are two things to mention. By default, the TCP window size field in the header is only 2 bytes, allowing to store a value of maximum 65K. In modern systems, this is not sufficient to handle high bandwidth networks. For that reason, there's a mechanism called TCP window scaling. Basically, during TCP handshake, if both sender and the receiver support window scaling, they can set an option in the TCP header called window scale. It's a number that indicates how many times the window size should be multiplied by 2. For example, if the scale factor is 3, then the final window size will be TCP window size times 2 to power of 3, that is window size times 8. This allows the window size to be as large as 1 GB. You can check if your Linux system has window scaling enabled by executing sysctl command. Second thing to mention is that the sender can send data until the receiver advertised window size is reached. That is not entirely correct. There's yet another condition when the sender will not send data. It's when the network is congested. Whatever comes first. We'll talk about network congestion shortly. Finally, we reach the fundamental and probably the most important TCP mechanism, that is congestion control. Let me draw a simplified diagram of a network. We have few nodes interconnected with few routers. Each router has a buffer to temporarily store packets when they arrive at higher rate than the router can immediately process or transmit. This can happen due to various reasons. For example, slow receiver, different link speeds, hardware failures, or performance issues. Now, if every node would start sending data at maximum rate, then the whole network would become congested. Router's buffer would overflow, and in turn, router would start dropping packets. TCP would start retransmissions that in turn would cause another round of lost packets, and eventually the network would collapse. How come today internet still works? It's due to congestion control mechanism that regulates the rate at which sender transmits the data over a TCP connection. It ensures a fair share of network resources and maintains overall network stability. When the network conditions are good, the congestion control algorithm successively increases the amount of data put on the wire. However, congestion control looks for certain signals. Usually it is packet loss and slow down the transmission rate if the signals appear, not to congest the network. Here are the basics of TCP congestion control. There is a variable called TCP congestion window that is maintained by the sender. Unlike receive window size, congestion window is not advertised to the other end. Congestion window represents the number of bytes that the sender is allowed to transmit without receiving an acknowledgement back from the receiver. During TCP connection, the congestion window is dynamically adjusted based on the network conditions and certain signals. Usually, the initial size of the congestion window is 10 segments. We can check the congestion window of the actual TCP connection with the SS command. SS command shows the actual congestion window in segments, so in order to get that in bytes, we need to multiply congestion window by MSS, that is segment size. Different congestion control algorithms like TCP Reno, TCP Cubic, and others define specific rules for adjusting the congestion window variable. In the simplest case, we can distinguish a few phases of the congestion control. First, we have a slow start. During this phase, congestion window, that is the amount of data that we can put on the wire, grows exponentially. Basically, the variable doubles every time acknowledgement is received. This allows TCP to probe the network to find the available bandwidth. Congestion window will grow exponentially until either slow start threshold is reached, or receiver advertised window is reached, or packet loss is detected. If the slow start threshold is reached, the congestion avoidance phase starts. In this phase, the congestion windows grows linearly by adding one segment for each acknowledgement received to avoid triggering congestion. If packet loss is detected, it indicates network congestion. Slow start threshold is set to half of the congestion window. Depending on the algorithm, the congestion window is reduced. For TCP Reno, that is an algorithm from 1990, if the packet loss was signaled by 3 dupACs, then congestion is mild and the congestion window is reduced in half and it starts growing linearly. If, however, congestion is signaled by acknowledgement timeout, then congestion is considered severe and the congestion window is set back to the initial value. By adjusting the congestion window, TCP dynamically responds to network congestion. In 2006, an improved version of the congestion control algorithm was introduced called TCP Cubic to respond to network congestion more efficiently. The main differences are use of cubic function during congestion avoidance phase to regain lost congestion window more efficiently. TCP Cubic calculates target congestion window based on time elapsed since the last congestion event and available bandwidth. It then adapts the congestion window based on the difference between current and target window size. Overall, TCP Cubic offers a more scalable and stable congestion algorithm compared to TCP Reno. TCP Cubic is the default congestion control algorithm in Linux kernel since kernel 2.6. Our small lab consists of 2 physical nodes. We'll use the iPerf tool to measure network throughput. Node 2 is running iPerf server and node 1 is running iPerf client. Nodes are connected to the same 1 GB switch. We'll be checking how packet loss and delay affects throughput for TCP Reno and TCP Cubic. In order to get some data, I did install InfluxDB. That's a time series database that will store our results, as well as Telegraph, a server-based agent for collecting and sending metrics. Here's a basic Telegraph configuration for iPerf. Command indicates command to be run on the server. In our case, we'll run a 3-second iPerf test from node 1 to node 2 and asks for the results to be in JSON format. Please mind that by default, iPerf performs a send test where the client sends data to the server. That's exactly what we want. Interval indicates how often the test should be run. The timeout indicates how long to wait for the result. We also tell the job that the provided data will be in JSON format and ask to parse a chunk of the JSON called end. Lastly, we'll override the metric name. After we restart the service, Telegraph will run our 3-second iPerf test every 10 seconds and store the results in InfluxDB. Let's switch the congestion control algorithm to TCP Reno by executing sysctl command. Last step is to visualize the results in Grafana. I have InfluxDB data source configured and a dashboard presenting 4 parameters: throughput in megabits, congestion window size in bytes, round trip time minimum, mean and maximum, retransmission count. As you can see, in ideal conditions there are 0 retransmissions, around 6 millisecond round trip, the congestion window is about 2 megabytes, and the throughput is around 900 megabit. Let's introduce a 20 millisecond delay. I'll be using Net Emulator for that purpose. As you can see, the round trip time increased accordingly to around 26 milliseconds. In order to keep the data rate, TCP had to increase the congestion window significantly. It's now around 6 megabytes. Let's see what will happen if we introduce 1% of packet loss on top of the delay. Throughput dropped to around 30 megabits. We see around 200 retransmissions, and the congestion window is only 35 kilobytes. Let's switch to Cubic and perform the same exercise. Okay, here we are. Cubic, ideal conditions. First thing we notice in comparison to Reno is that the congestion window did shrink from 2 megabytes to half a megabyte. Also, round trip did decrease to around 2 milliseconds. Let's introduce a 20 millisecond delay. Congestion window did increase to around 4 megabytes. Let's introduce 1% packet loss. The results are around 100 megabit, 300 kilobytes congestion window, and 150 retransmissions. Now the fun part. Both Reno and Cubic react to packet loss as a signal to limit transmission rate. Let's switch to BBR, algorithm that is developed and used by Google in their GCP and YouTube services. BBR stands for bottleneck bandwidth and round trip time. BBR does not look at packet loss, but bandwidth and packet delays. It can cause significantly more retransmissions. In order to enable BBR, we need to modify 2 parameters. See what happened. Throughput is 750 megabit. Congestion window is around 5 megabytes, and the number of retransmissions is 1500. That is almost like there was no packet loss. Amazing. Let's go even further. We'll increase the amount of dropped packets to 5%. It can still keep up with 500 megabits. Outstanding. Moreover, if we switch to ideal conditions, we see the round-trip time is 1 millisecond and the congestion window is only 350 kilobytes. BBR congestion control algorithm is the future of the internet and you should use it now. Google did already release version 2 of BBR that should be more fair to other algorithms, although it's not there yet in the mainline kernel.